Hey everyone, and welcome. Let's talk about hash tables. You know what really breaks them isn't the big idea, it's the tiny details. One wrong move and that lightning fast performance you're counting on, it just grinds to a halt. So today we're going to dive into those common traps and, more importantly, how to get out of them.
Ah, oh, one. This is the dream, right? Constant time. It's the whole promise of the hash table. This idea that you can find, add, or delete anything almost instantly, no matter if you have 10 items or 10 million. I mean, that's why we use them for everything. Databases, caches, those dictionaries you use in Python or Java, they all rely on this magic. But here's the thing, that promise, it's surprisingly fragile. Just a couple of really common, easy-to-make mistakes can completely shatter it. And suddenly, your instant O1 lookup becomes a slow, painful ON search, where you have to check every single item. So how does this even happen? And how do we prevent it? Well, let's first get on the same page about what that O1 promise is all about.
Right, so before we can talk about breaking it, we gotta know how it's supposed to work in the first place. What is this speed promise, really?
Okay, picture this. You've got a huge shelf with a bunch of numbered boxes on it. Each box is what we call a bucket. Now, when you want to put something away, you don't just shove it into any random box. Nope. You use this special rule, that's our hash function, and it tells you instantly which box your item belongs in. So later, when you need to find it, you just use that same exact rule, go straight to the right box, and boom, there it is. No searching. That's the O of 1 magic in a nutshell.
That all sounds perfect, doesn't it? But in the real world, things get messy. So let's pull back the curtain and see what happens when this perfect system starts to break down. It turns out, when your hash table's performance starts to tank, you can almost always blame one of two specific problems. Think of them as the two villains who are secretly trying to ruin your O of 1 speed. So villain number one is collisions. This is when your hash function points two different items to the exact same box. Now you've got a little queue forming inside that one box. A couple of items in one box, no big deal. But when that line gets too long, you're basically back to searching. And then there's villain number two, crowding. This is when the entire shelf of boxes is getting stuffed. You're just running out of space, and there's nowhere to spread things out nicely anymore. And what's cool is that we can actually measure this crowding with one single super important number. It's called the load factor, usually shown with the Greek letter alpha. It's a simple fraction, the number of things you've stored divided by the number of boxes you have. Think of this number as your personal early warning system. And this is exactly why you have to pay attention to that number. Just look at what happens to your search time as that load factor gets closer and closer to 1, 100% full. It doesn't just get a little bit slower. The time it takes to find something literally explodes. It goes up exponentially. At this point, your O of 1 performance is completely gone. It's a memory. So the takeaway is clear. We have got to keep that load factor under control. Okay, so we've met the villains, we know what's trying to wreck our performance. Now for the good part. Let's talk about the two critical fixes we can use to fight back and get our speed back. The game plan here is actually pretty straightforward. Step one, we need a smart way to deal with collisions because they are going to happen. Step two, we need a firm rule for controlling that load factor to stop crowding before it starts. So let's tackle these one by one. When it comes to handling collisions, you've basically got two main approaches. The first is called separate chaining. This is like if a box is full, you just start a little linked list inside that box. It's great because it handles getting full pretty gracefully, but the downside is it uses a bit more memory for all those pointers. The other way is open addressing. Here, everything stays in the main array of boxes. If your target box is taken, you just look for the next empty one. This is awesome for your computer's cache, but, and it's a big but, performance falls off a cliff as the table fills up. And what about fixing crowding? Well, the solution is just beautiful in its simplicity. You resize. You pick a limit for your load factor. A common one is 75%. The second you go over that limit, you just create a brand new table, usually twice as big, and you move every single item over. It's literally like realizing your shelf is full and just going out and buying a bigger one. It keeps everything nicely spread out and makes sure your lookup stays super fast.
Okay, so we've talked about collisions and we've talked about crowding, but there is one fundamental rule, an unbreakable law that the entire idea of a hash table is built on. And if you break this rule, honestly, nothing else we've discussed even matters.
And here it is. This is the golden rule. Keys that compare as equal must produce the same hash value.
That's it. It's a non-negotiable contract. Your definition of equal and your hash function have to be perfectly in sync.
So why is this a huge deal? Well, imagine you break this rule. You put an object into your hash table, and the hash function says, okay, that goes in box 20. Then you come back later to find that exact same object, but this time, for some reason, the hash function says, oh, that should be in box 45. Your object is still in there, somewhere, in box 20, but you'll never find it again. It's lost forever. Your hash table is basically corrupt.
All right, let's wrap this all up with some super practical advice. Let's say you're in a technical interview and they ask you to design a hash table. Here are the things you absolutely have to talk about to nail that question.
First thing out of your mouth, your resizing policy. Just say it. I'll resize when my load factor hits 0.75. Done. Next, pick your collision strategy and explain why. Are you going with chaining because it's robust, or open addressing for better cache performance? Third, you have to mention deletions. This is a big one. Especially with open addressing, you need to talk about using tombstones to mark deleted spots so you don't accidentally break your search paths. And of course, bring up that unbreakable contract between equality and hashing, and be ready to talk about all the trade-offs: memory, cache, performance. Show them you've thought it through.
So when you peel it all back, the magic of O1 isn't really magic at all, is it? It's just a promise that you keep through smart, careful engineering, by handling collisions, by controlling that load factor, and by never, ever breaking that fundamental contract. You're the one who makes sure your data structures stay blazing fast. So the only question left is, now that you know the rules of the game, how are you going to build your next hash table?